In this video, we will talk about how to solve ordinary differential equations in Mathematica, similarly to the previous video, except this time we will explicitly code up the numerical methods. And in particular, in this video, we're going to focus on Runge-Kutta methods. So let's suppose we have an ordinary differential equation of this form. dy by dt equals f, some function f of t and y. And here y can be considered a scalar function or scalar parameter, and f is some scalar function of t and y of t. And remember, y depends on the parameter t, which could be time. And so we can write more explicitly this dependence as f of t and y of t, like so. But f can also explicitly depend on time t. One of the first methods that comes to mind for solving such a system numerically is the Euler method, which is based on a Taylor expansion. So let's consider a Taylor expansion of the function y that we want to solve for. So if I use the command series and expand the function y of t, I can expand with respect to the parameter t about, let's say, some initial time t0, or let's call it t1. And let's suppose I want to keep terms of order 2 in the expansion. Then the series or the Taylor expansion looks like y of t1 plus the derivative at t1 times t minus t1 plus 1/2 the second derivative times t minus t1 squared plus terms of ordered 3. So if I want to go, let's say, from some initial time t1 and integrate up to some time t2, I could just write t2 here and t2 here. So this is an approximation for y of t2, essentially. So let's assume that I want to keep the lowest order correction. So this is the lowest order correction, and I can ignore high order corrections like of order t2 minus t1 squared and so on. So first of all, I can simplify this a little bit. I can say normal. That will get rid of the order t2 minus t1 cubed term. And I can also do a substitution and say t2 substitute by t1 plus, we can call this h, or we can call this delta t. Let me make sure that this symbol is cleared before I use it. Didn't quite work because the normal command affected this substitution, so I can put this in parentheses and execute again, and now it worked. So we see that t2 minus t1 got replaced by delta t here and delta t squared here. So essentially this is an approximation for as I said, for the next time step, y of t2 given y of t1. So we can use this in a time stepping scheme. And let me just write this a little differently. So instead of t1 and t2, I can use tn and tn plus 1 to make it more obvious that this is a time stepping scheme. And I'm approximating y of t1 by expanding around y of tn. And then I'm going to replace again Tn. It's going to be replaced by Tn plus delta T. So it's essentially the same command as here, just replacing the symbols that we use to represent time. Okay, so just to be concrete, we see that the derivative of y respect to Tn is already showing up in the differential equation. So that's the basic idea of the Euler method, is to replace the derivative with the function f. So this leads us to this approximation. So let's replace this derivative with f of Tn and y of Tn. And we arrive at this scheme. We have yn plus this correction, which is the first order correction from the Taylor expansion that's linear in delta t. And then there are corrections of higher order, which at the first approximation at leading order we can ignore. So this leads us, as I said, to the Euler method. Let me paste this. Let me paste this correctly. Okay, so the Euler method is essentially a Taylor method of order 1, and it consists of approximating y of Tn plus 1 with y of Tn plus delta t times the function f, which appears here in this differential equation. Okay, so we can also rewrite this a little differently. So this is essentially a Runge-Kutta method of order 1, or Rk1 for brevity. So the scheme that we can use to evolve this differential equation numerically consists of an initial condition, which we always need for an initial value problem like this one. So this is a first order ordinary differential equation, which means we need one initial condition on y. So let's assume that we start from some initial time t0, and the value initially of y is y0. So that's the first value of y, the first time step, and then we can compute the derivative y dot, which is given by f according to the differential equation, and multiply by delta t to compute this term. So this term we call it k1, and then we simply add k1 to y of Tn and get the next step. And we can do this for n equals 0. This will give us y1 from y0 plus the correction. And then we can do it for the next value of n, which is n equals 1, will give us y of t2 equals y of t1 plus the correction, and so on. So we can put this in a do loop and time march forward. So we can march forward in time up to some final time tm. Okay, so let's see an example of how to do this. In the previous video we discussed a very simple linear equation that was x dot or x prime equals x. So in this case, let me just rewrite this a little bit for clarity. So let's call this y, let's call it x, and let's call this x. Okay, so I just replaced y by x for clarity, and let's copy this equation down here just to see things more clearly. So we see if we're solving this equation, then all we need is the functional form of this function f. And in this case, f of t and x is simply equal to x of t, obviously. So we can apply this scheme directly. All we have to do is replace f of x by x. So let's try and do that. Now I have a comment here. We could set up a set of time points or time grid using this symbol Tn, and so you could use T0, T1, T2 and so on to store the moments in time that we're using to evolve the system. However, that would be a bit wasteful because Mathematica would then have to store in memory each of those quantities T0, T1, T2 as symbols, and symbols take more memory than numbers, so this would be slow and consume unnecessarily a lot of memory. So it's more efficient to store the values of the time and of the values of y or the values of x as vectors or arrays. So to do that, let's set up a grid. Let's set up some vectors of t and x, essentially. So first of all, let's recall from the previous video when we solved this differential equation with this initial condition, we got an analytic solution which is e to the t. So that's one of the simplest differential equations you can come across, and the initial condition is x of 0 equals 1. So let's assume that the initial time is given by 0 and that the final time is given by 1, and then let's suppose that we want to evolve for 100 time steps. So m is the number of time steps that I want to evolve for, and then that means that the time step, I can use the palette to hit this delta t, will be given by t final minus t initial divided by the number of time steps m. And then if I want the time stamps or the time moments, I can use the range command. So we go from ti to tf in steps of delta t, and let's try that, and indeed we see that we get a vector of the time moments that are 0, 1 over 100, 2 over 100 and so on. They are in steps of 1 over 100 and they go from 0 to 1 as expected. And to convert this to a number for efficiency, we prefer floating point numbers. We can use /n, and now our time moments are floating point numbers. So let's save this, and then let's define a vector x which will store the solution at each point in time. So let's start with you can use constant array to zero out a vector, and then we can determine the size of the vector to be, it has to be the same as the size of the time vector, because each of those time moments will correspond to one value of x. So each value of t will have a corresponding value of x of t. So let's use m+1 here. And we need m+1, not m, because actually the number of steps is m+1, and we can check that they are the same. So if I use length of t and then length of x we can check that they're both given by 101. Okay, so m is the number of spaces that we divide by, and that's 100, but the number of time steps is 101. Okay, so now we have set up our vectors. We have initialized this vector x to be 0 everywhere. Of course, that's not the correct value, or it's not the correct initial condition. So the first thing we need to do is to set up initial condition, and then start this do loop right here. So let's suppress these outputs, and let's delete this. Now to initialize the first value of x is x1, of course, and that's 0 for now, but we want to set it equal to 1 because that's the correct initial condition. So we can just do this by hand. So x of 1 is 1.0, and then we can start our do loop. So the next value is n plus 1, and that would be equal to, well, let's write it like this. So let's first evaluate a k1. So k1 equals delta t times this function, and we just argued earlier that this function is given by f of t and x equals x. So this will simply be x over here. So it will be x of tn. So in this case, that means it's xn. And then the next step is to simply add that to xn, like dictated by this formula. So xn plus 1 will be xn plus the correction from the Taylor expansion, which is delta t times f, which in this case is delta t times x, or in other words, it's simply k1. Okay, and that's the end of the loop basically, and then we simply need to specify the values of n. So the first value of n will be, let's see, so x1 has been evaluated already, so the next value will be x2 that we need here. So we start from n equals 1, and that will plug in n equals 1 here and compute x2. So the second element of the vector x, and the last value of n will be m minus 1. Okay, so let's try this loop. So it printed the first value of x, but it will not print these values of x unless we ask it to print them. So let's just suppress this output, and I can simply type x and see all the values, and we see all the values of x here. So we start from 1, and then well, let's see, actually the last value did not get updated, so let me just correct this. So let's go up to m. Okay, so these are the values of x that we see. So we can plot this result if we want to. So for example, I can do list plot of x, and we can see the solution. Now if I just do list plot of x, it's going to show me the values of x, and here we're just going to have the first element, second element, third element. So that's just the number of each element of x, and because x has 100 elements, this axis goes from 0 to 100. But that's not the most useful thing. Ideally, we want the parameter t, the time, to show up here. So to do that, as you hopefully recall from the first few videos, we need to pair up t and x, but we can't do that like that. We need to transpose. So that will create pairs of t1 x1 and t2 x2 and so on. So now I can put that into a list plot. So let me delete it from here and put it in here. And now this axis stayed the same. We have the values of x, but this axis now has the values of t, which goes from 0 to 1. If I want to plot the axis labels, we can use the command axis label, and we can put t and x. And then we can plot this against the exact solution, which, as we showed earlier, the exact solution is e to the power t. So let's plot e to the power t from ti until tf, and let's suppress these and combine them. So we can use show, and let's use %% for the previous output and % for the last output. Okay, and now we have both these plots together. Let's change the color of this one. Let's do it red. Okay, and now we see the exact solution is given by this red line, and the numerical solution from Euler's method is given by these blue dots. And we see that the accuracy is reasonably good for a first order method, but it starts to drift away as time goes by. And in fact, if we want to see how much it drifts away, we can do this plot. We can simply plot the difference between x and e to the power t, the exact solution. And I know that if I use exponential of t, I know this will give me the exact solution at each time t, because this is a grid of the time points. So I can simply subtract this from the numerical solution, and I should change the label here to be delta x, because this is the error in x, and you can see now that the error is around 10⁻³ or 10⁻², and it increases as time goes by, which is what we would expect for a first order method like this. We can try and improve accuracy by increasing the number of time steps or decreasing the number, the spacing, delta t. So let's try, we're keeping the interval fixed, so we'll still go from 0 to 1, but instead of 100, let's try 1,000 steps, and let's repeat the do loop. And now you see that the red dot, the red line and the blue dots overlap, and if we plot the error, it's quite a bit smaller, but still it's one order of magnitude smaller, perhaps, but not a lot smaller. So basically every time you increase the number of steps by 10, you improve the accuracy by 10. As we just saw, this just changed by 1 digit. And this is what we expect for a first order method. The error is of order delta t for a first order method. Okay, so with that in mind, let's move on to a higher order method, which is a bit more useful. So if we inspect this again, the Rk1 method is given by this scheme right here. So we have a correction of order delta t to add in each time step. A method that's of order 2, there are more than one methods of order 2, but one of them is given by this scheme right here. So in this case, we compute again the initial data as before, and we compute the first order correction in the Taylor expansion, but then we also compute a second order correction. And you can prove, if you want to, that this is consistent with a second order Taylor expansion. We're not going to do it here, but I'm just going to provide the scheme. So if we compute K1 as before, but then also compute an extra step, K2, then the correction to go from y of tn to y of tn plus 1 is given by this formula right here. So again, let's try and replace y by x for simplicity, just so we can make a more easy comparison. So let's rewrite the scheme here. Okay, so this is a differential equation we're solving, and again, if we compare the general formula for the differential equation and the scheme, we see that f of x has to be equal to x of t, as we just saw before. So let's quickly code up this scheme. I can start from the same place that I started before. So let's copy all of this code down here. And let's stick to 100 steps. And now the scheme tells us to compute K1, which we already did before, but now we have to do an extra step and calculate the K2. And that's going to be given by delta t times f of x plus K1 over 2. So because f of x equals x, all I have to do is replace this function here by x of tn plus K1 over 2, and then comma. So this is it really. We still need to make this correction. So the correction here for the next time step is K2. And keep in mind that in our system, the one we're solving now, does not have an explicit dependence on time t, which is why I didn't need this correction or this correction. But in general, if you have an explicit dependence on t, then you have to make sure to include these corrections here. Okay, so let's rerun this, which sets up our grid just like before. And now let's run the second order scheme here. And let's see if the accuracy got any better. So we see that the accuracy looks better. So the overlap looks better, although we just use 100 time steps. And again, let's try and rerun this to look at the error. And we see now that the error is quite a bit better compared to what we had before. So before we had an error of 10 minus 3, and that was with quite a bit, with 1,000 points. And if we use the 100 points, the error was quite large. It was 0.014, whereas now with the same number of points, the error is 0.00004. So this is what we would expect for a second order method. So the Runge-Kutta method of Rk2 is second order accurate, which means the error is of order delta t squared. The next method one can consider is a third order method. I'm not going to implement that. Instead, I'm just gonna give the formula in case you want to try it. But it simply involves an extra step. So we have a K1, K2, and a K3, and each of those Ks are computed recursively. So you compute K1, you plug it in here, you compute K2, then you use that K2, you plug it in here, compute K3, and then the correction for the next time step is given by this combination of K1 and K3. So remember, K1, K2, and K3 get overwritten in each time step. You don't need to store them. You just need to store the values of y, which is the physically interesting quantity that you want to plot later. But K1, K2, and K3, you don't need indices in them because you can simply overwrite them and save memory. So I'm not going to try Rk3. Instead, I'm going to move directly to the more popular method, which is Rk4. So that's a fourth order Runge-Kutta method. It involves one extra step compared to Rk3. So again, we have K1 and K2. Up to here, the method is the same as the Rk2 method that we just implemented right here. So the first two steps are identical. Then you have two extra steps, so each step increases the order by one. So you compute K3 and you use K2 in here, and then you use K3 inside here to compute K4, and then the correction, the next step is given by this combination here, 1/6 of K1 plus 2K2 plus 2K3 plus K4. And you can wrap that inside a do loop and implement it. So let's try that again for this case, for the exponential growth. And again, for clarity, let me replace this x by y everywhere. So that will make it easier to see what our quantities are. So again, for the same reason as before, if we try this for this exponential differential equation, x prime equals x, then you immediately deduce that f of t and x is x. So let's try and implement this. So we can write down the implementation basically. So this is the implementation of Rk4. Again, the first two steps. So first we have the time step, the initial condition. Then we have K1 and K2 just as before. And f of x is simply equal to x, which is all we have to do is replace f of x by x in all of these equations, and then that's our scheme. And then in the end, we simply implement this formula, so we have the combination of K1, K2, K3, and K4. And let me copy paste the time grid that we constructed earlier. Okay, so let's do again 100 time steps, and then let's do the do loop, and then we can simply reuse all of these commands to do the plots. And we have a good overlap, and now the error is much better So we see that we have accuracy up to about 10 digits. So the error is of order 10 to the minus 10. And this is the sort of accuracy we expect for a fourth order method, which is Rk4. And that's essentially one of the reasons why the Rk4 method is so popular. You can quite easily, with only a minimal effort, with only minimal effort, you can get quite a bit of accuracy. Now you could try and make this even better by increasing the number of time steps. Obviously, let's try 500. And let's repeat this. And then the error is getting better as we expect. Okay, so this was an example of applying the Runge-Kutta method to a scalar ODE with a one parameter, like x dot equals f of t and x. The question is, how do we apply such a scheme to a system of differential equations? So to do that, let's again consider the harmonic oscillator that we considered in the previous video. So in the previous video, we showed that we could take a second order system. So the system, let's write it down again. It was x double prime equals x of t. And we had initial conditions x of 0 equals 1 and x prime of 0 equals 0. And the unknown was simply x of t. And actually there was a minus here. And that was the solution x of t to the system given these initial conditions for the second order differential equation. Now, the Runge-Kutta methods I described apply to first order systems. So the easiest thing to do would be to reduce this second order differential equation to a first order system. And we can do that by simply setting x prime of t equal to some other quantity p of t. And this is what we do here. And if we do that, then x double prime of t will simply be p prime of t. So this equation will become p prime of t equals minus x. So that will give us two equations that are first order. That means only first order derivatives show up here. We have first order derivatives in time. But the price we pay is that we have to use two equations now instead of one. So that's the first order reduction of a second order system. And the initial conditions are the same as before, except x of 0 is again 1, but now p of 0 is simply x prime of 0, which has the same value as before, so p of 0 is 1. And if we use dissolve to construct the solution, Mathematica gives us a solution that's the same as before for x of t, but it will also give us the solution for the derivative of x prime of t, which is p of t. So for more details, you can go back and watch the previous video. But now we want to solve this system numerically. So the way to do that, well, first let's do it using an Rk1 method. So let's set up a grid like before. So let's go from t initial 0 up to t final equals 10 pi. We know one period is 2 pi or 2p. So this is 5 periods essentially. And let's try 100 or 1,000 time steps. And again, we define the time step and arrange for time values. And then we set up a grid on X, this is basically a vector that stores the values of X at each time instant, and this is another vector that stores the values of P at each time instant. Now, many people use some construction which is called append to, and they append a value after each time step. I prefer not to do that because that leads to complications and loss of efficiency, because you have to change the size of that vector. So I prefer to avoid that, and it's error prone basically. So instead I prefer to work with fixed size vectors, and I can simply update their values. I can set everything to 0 initially and then update the values of x and p as we go forward in time. So that's what we're going to do inside the do loop. So our do loop will look very similar to what we had before for the exponential ODE that we solved, except now we need two initial conditions, one for x and one for p. So these are our initial conditions: x of x at time 0, that's the first element of this vector, is 1, and p at time 0, which is the first element of this vector, p, that is 0. And then inside the do loop, we update the values of x and p according to the Taylor expansion, basically. So remember, the differential equation is x dot or x prime equals p. So the Taylor expansion here would be xn plus 1 equals xn plus delta t times x dot. But x dot equals p, so I'm simply replacing x dot by p here. And similarly, in this equation, we have pn plus 1 equals pn plus delta t times p dot. But p dot is minus x. So that's the first order correction from the Taylor expansion that comes into here. So essentially, this is the Euler method, which is, as we argued earlier, the Euler method is a Taylor expansion first order, or it's equivalent to an Rk1 method. So let's try and execute this do loop. So the loop goes from 1 to m, and I hit shift enter, so it has been executed. And we can use list plot to look at the solution, and it looks a little strange. Okay, so it looked a bit strange because I hadn't executed all commands. So let's try 1,000 time steps. Okay, and we see that we see some kind of drift. The amplitude of the oscillation starts increasing with time. This is obviously not a very good sign. As discussed before, we want the time here, so to do that we can use list plot and use a transpose to put the time data and the x data here. And if we do that, then we have t on this axis. So let's get rid of this command and just keep this, and then we can plot this against the analytic solution. And we can use show to show these two together. So let me suppress this with comma, suppress this with comma, and show these two together in the same plot. And we can use plot style, and let's choose green. Okay, so the green line is the exact solution, and the blue dots are the numerical solution. And although initially the solutions look close together, as time goes by, the numerical solution gets worse and worse. And that's of course to be expected for a first order method. And we can also plot the difference if we want to look at the error. So again, I'm doing a list plot transpose, and I'm subtracting the exact solution cosine of t from the numerical solution. And we see that the error gets larger as time goes by, and what gets quite large actually. Obviously we can use more points, so let's try 10,000 points and run the loop again and try these plots again. And now the overlap is better, the solutions stay closer for a longer time, but still there's a drift. As time goes by, the solution, the error increases. It's actually interesting to look at the phase plot of momentum versus time. So to do that, we can use a list plot, and instead of x and t, we can use p and x. So let's actually copy paste this. So we can use x here, and we can use p here, and x here and p here. And we can see that this is not quite a circle as it was when we solved the system analytically. This is also a bit squeezed, but that's because the aspect ratio is not 1. So we can use the command aspect ratio and then 1, and that will make sure that the x and y axis have the same dimensions, the same scale. And we can combine this with the parametric plot that we showed in the previous video. So let's do parametric plot. So this is the exact result, and it's a perfect circle, a unit circle in phase space, but this is basically a spiral instead of a circle. So to see that more clearly, we can again, let's go back and reduce the number of time steps and execute again. And we see very clearly what happens. So we start at x equals 1 and p equals 0. So that's a spring that I just pull and then release with zero speed, and then that is going to oscillate. And if there's no friction, it's a harmonic oscillator. It should go around with constant energy, so it should go back to the same point where it started after each cycle. So that's where the spring starts, it goes around like that, and then it reaches the same point it was before. But the numerical method violates these physics, so instead we end up with more or less energy, and here actually we have more and more energy that's artificially injected into the system because our numerical method is not very good, it's just first order in time. So to simulate this system a bit more accurately, we can use a second order Runge-Kutta method, or third or fourth order. So let's try that. So to write down a higher order method, let's just recall our system has this form, and let's write down an Rk1 method, which we wrote earlier. If you want to look at a proof of this method, of how this is equivalent to a fourth order Taylor expansion, you can go to Wikipedia and look at the Runge-Kutta methods, and there's a proof there for the fourth order Runge-Kutta method. Now the way it's written here, it's written for a one parameter system. So our one parameter is x, and we have one function f of t and x. If we want to consider a high order system, we can consider x to be a vector and f to be a vector. But let's start simple, and then k1 would also be a vector. So you could write your code like that. But let's, for this video, we're gonna keep this a bit simple for reasons that will be clarified later. Let's suppose that instead of this system, I have a system that is a system of two differential equations. and we have an equation dx by dt equals f, and equation dy by dt equals g. But these functions are functions of t, x, and y. And again, g is a function of t, x, and y. Okay, so that's a 2x2 system, 2 equations for 2 unknowns, x of t and y of t, that we have to evolve. And obviously there are 2 initial conditions, one for x and one for y. So these are our initial conditions here, and then the scheme to evolve that is basically very similar to this, except if f is a vector and k1 is a vector, we can simply write that down as the first component of the vector would be k1, and the second component of the vector would be L2, and k1 would be given by delta t times this first function, and L1 would be delta t times this function g. And the arguments here are the same in both cases. It's only the function f and g changes to compute k1 and L1. So we simply double this line with another line that has k1 and L1. And then the other expressions simply get one more counterpart. So k2 gets another counterpart, L2, and k3 gets another counterpart, L3, k4 gets another counterpart, L4, and so on. And then in the end, the final time step, the next step for x is simply this. It's the same as before, where we use all the k's to update x. So all the k's get used here for the first equation, and then all the l's that we computed get used in the second equation, since these were used to computing L was done using the function g. So naturally, all these L's will be used to update the second equation, dy by dt equals g. So essentially, this is following a Taylor expansion to fourth order, and eliminating all the derivative terms in terms of just values of f and g, so that you don't have to evaluate derivatives. Okay, so let's try and code up this scheme for the harmonic oscillator. It looks a bit messy, but it's very straightforward, and we will see simpler ways to code this up in the future. But for now, let's just code this up explicitly for the harmonic oscillator. So let's start with an evolution. Again, same as before, we go from t initial 0 to t final equals 5 periods, or 10p, and let's use 100 time steps. So delta t is tf minus tii over the number of time steps. We set up a time grid, we set up a vector for the values of the position, and a vector for the values of p. And now let me just write down the Rk4 scheme. So our initial data is the same as before, x equals 1 and p equals 0, and then we'll have a do loop. So our do loop will start with a k1, and remember what the system looks like. So dx by dt equals p, and dy by dt equals, but remember p is the momentum, and in this case p is y, and then the other equation is dy by dt equals g, and that is equal to minus x if you look at the equation we're solving here. So the second equation is dy or dp by dt equals minus x. So that means we already know the functions f and g. So f is equal to y and g is equal to minus x. So all we have to do is simply replace the functional form of f and g in this scheme by what we know applies for this system. Okay, so the first equation will be k1 equals delta t times f, and we know that f equals y or p. So the first equation will be simply k1 equals delta t times p. Let me delete this for now so we can see this more easily. Okay, so the second equation will be L1. So L1 will be delta t times g, and g is minus x. So that will be x of n, and we will have a minus. And then next we need to code up k2 and L2. So k2 will be given by this expression. It will be delta t, and then f of x and y, but this is just y, which is p. So in place of p, we put a pn plus 1 plus n L1 over 2. So, or actually p of tn plus n1 over 2. So let's copy this. So we have pn plus L1 over 2. And then similarly, so actually that is k2. Let's be careful. And then we have L2 equals this expression. So this is delta t. And then remember, the L2 is given in terms of g, and g is simply minus x. So we're gonna take minus x and replace x by by x of tn plus k1 over 2. So this will be x of tn plus k1 over 2 and comma. So you can similarly follow the other terms. All you have to do in each case is replace f by y and g by minus x and just apply these formulas. For the harmonic oscillator, in this case, it's not time dependent, so this first column, the first argument of t is not needed, but you need the other arguments. So I'm simply going to write down the next two steps. So k3, L3, k4, L4 are given by these expressions. They're just very similar. So remember, so k2 and L2 show up here in the calculation of k3 and L3, and then these quantities k3 and L3 are used to calculate k4 and L4. And then finally, the next time step will be given by these expressions. So that's the first expression for x, which we use k to update x for the reasons we just mentioned before. And then we use L to update the momentum p. And then the time steps go from n equals 1 up to m. Okay, so now let's rewrite this these vectors, the construction of the vectors t and x and p. So let's plug those in here, and let's just do 100 time steps and see what happens. Okay, so the shift enter, the loop is executed, and then we can simply copy paste these commands to look at the results. Okay, there seems to be something wrong here. Okay, so there seems to be a sign error here in L2. Let's try that again. Okay, that's much better. So we see that the numerical solution in blue, the blue dots overlap with the green analytical solution quite well. And the error is much smaller than before, is around 10 to the minus 3. Whereas here it was quite large. And let's do the phase plot, the phase portrait, and let's see if this spiral gets any better. So let's just put that under here. Okay, and actually we can suppress these and put them together. And we see that actually these dots, they fall onto the unit circle much better, much more accurately than before. Although it looks like they fall onto the unit circle much better than before, it's not going to be exactly true. So to see that, we can plot, for example, the energy. So the energy coincides with the radius of this circle. It's proportional to p squared plus x squared, which is the radius of this circle. So we can actually do a list plot of let's see, we can do, let's start simply with x squared plus p squared, and we see that although we start from 1, we start drifting away. So that's a violation of energy conservation, basically. The energy is actually given by this quantity divided by 2. And if I want the time here, I can use transpose T, and then that's the energy. And then I can use axis labels. And the axis labels will be given by T and E. Okay. As we see, the accuracy gets better with Runge-Kutta fourth order method. Obviously, we can use more time steps. So let's try 1,000 time steps. So that will decrease delta T, and then conservation of energy is going to look much better. Let's subtract 0.5 from this to see the result more accurately. So we see that the energy violation is around 10 to the minus 9. But what's worrisome is that it increases linearly with time. Although this is a fourth order method, the energy violation is not fourth order, it's actually first order, so it's linear in time. So that's very worrisome. So if we try to evolve the system for longer, so let's try and evolve for 50. And let's increase the time steps proportionally. So let's do 5 times more time evolution, then we see that after a while the error gets large, so the error, the amplitude increases linearly, and the error in energy increases quite a bit. So that's one thing that we will explain that in a minute. But another issue you may come up with is if you increase the time evolution from T initial to T final. So if you evolve for longer, but you don't, let's suppose that we don't increase the number of points, that means delta T would now be larger because TF is larger, but we didn't change M. We keep it to 100. Let's see what happens. And what happens is instability. So the green plot here is the exact solution, and blue is the numerical solution, and as you can see, it's completely wrong. So Runge-Kutta methods require a relatively small step size of delta T. If you exceed some value, some limit of delta T, the methods become unstable. And we can study the stability of Runge-Kutta methods in another video. But for now, let's just keep in mind that if you see instability like that, you have to reduce your time step. Okay, and so let's go back and do that. So let's use more time steps, and then the solutions overlap, and there's no longer instability, there's just some numerical error, but at least the solution is more or less stable and looks more or less like a circle with a slight drift that we cannot see here, but we can see it here if we plot the difference of the energy from the exact result, then you see that there's a small error. Now, essentially the fundamental reasons why all these methods violate energy conservation has to do with symmetries of the underlying system. So let's go back here where we started from. As we discussed, the Euler method is given by this equation here, and you see that this equation has no symmetry. So although the underlying equation, the differential equation is dx by dt or dy by dt, this equation may have a symmetry with respect to time. If you change t to minus t, for example, it may stay the same. Just like the harmonic oscillator satisfies this condition. But this scheme does not respect that symmetry anymore. So if you change tn for tn plus 1, delta t will change sign. These two terms will change with each other, but tn will be replaced by tn plus 1. So this term here is not symmetric with respect to time reflection. And the same is true for higher order terms for the Taylor expansion, delta t squared and delta t cubed and so on. In a future video, we will discuss methods that are symmetric under time reflection, and we will see that in many cases, time symmetric schemes tend to conserve energy, either exactly or on average. Stay tuned for these other videos, which will be based on Taylor methods and Hermite integration methods. Thank you.